This section examines vehicle heating and ventilation systems. To improve driver and passenger safety, a supply of fresh air is necessary to reduce fatigue and maintain comfort. Fresh air is drawn from outside, usually through ducts at the base of the windscreen, and directed to the passenger compartment. The air is then delivered through ducts and flaps, which are positioned to direct air to particular points inside the passenger compartment. These flaps can be controlled by cables, by vacuum servos, or by electric servos. In this way, air can be directed to the face ducts, floor ducts, window demisting ducts, and rear passenger compartment ducts. A fan driven by an electric motor is used to assist the air to flow through the passenger compartment when demands are high or when vehicle speeds are low. In internal combustion engines, much of the heat generated is lost to the atmosphere or wasted. Some of this heat can be used to heat the incoming air to a comfortable level when required by the vehicle occupants. Engines that are liquid-cooled direct heated coolant to a heater core to heat the air. The heater core is a small radiator consisting of tubes, fins and tanks. It is mounted under the dash panel inside the air plenum chamber, where air can be passed across the core fins and into the vehicle interior. The heater core is connected to the engine's cooling system by flexible rubber hoses, which allow for movement and a reduction in the level of engine noise and vibration transmitted into the passenger compartment. The rubber hoses are fabric reinforced to resist cooling system pressure and temperature. The coolant flow is created by the engine water pump, directing the coolant through the heater core and then back to the engine. A heat control valve is located in one of the heater coolant hoses to adjust the quantity of coolant flowing through the heater core. The valve can be operated by a cable and lever system. A lever mounted on the vehicle's dash panel is connected by a cable to another lever on the heater valve. Movement of the dash lever is transferred through the cable to the lever on the heater valve. With the dash lever in the maximum heat position, the valve is fully open, allowing the maximum amount of coolant to circulate through the heater core. When the engine is at normal operating temperature, some of the heat in the heater fins is transferred to the air passing over them. The heated air can then be directed to raise the temperature in the passenger compartment. Moving the lever to obtain a cooler temperature setting reduces the valve opening. This restricts the amount of coolant flowing through the heater core. Less heat is then transferred to the air passing over the heater core fins. This section examines the basic principles of air conditioning. The function of the air conditioning system is to reduce the temperature inside the passenger compartment to a level that ensures passenger comfort. It achieves this by removing excess heat and transferring it to the outside of the vehicle. The removal of heat lowers the temperature and the vehicle interior becomes colder. Cold is simply a relative absence of heat, or can be regarded as a condition which exists after heat has been removed. Heat always travels from a hotter object to a colder object. This heat transfer can take place by one of three methods: conduction, convection, or radiation. Conduction is heat transfer by direct contact. Convection is the transfer of heat by circulation of convection currents in a gas or liquid. Radiation transfers heat in rays. For any given application, the air conditioning system must have sufficient capacity to remove the quantity of heat necessary to lower the vehicle interior temperature to an acceptable level. Since heat is a form of energy, it cannot be destroyed. The air conditioning process is simply one of removing heat from one place and transferring it to another. The temperature level arrived at is simply the degree of hotness or coldness achieved, and is usually measured on the Celsius scale, which has two fixed points. The freezing point of water, that is when it turns to ice, is the lower fixed point. The boiling point of water, that is when it turns to steam, is the upper fixed point. When water turns to ice, heat has been removed from the liquid water to bring about a change of state to a solid. That is, when sufficient heat is removed from a body of water, its temperature will reduce to 0 degrees Celsius, and it will remain at 0 degrees until all the water has changed to its solid state, ice. For water to boil, heat has to be added to the water. While it is boiling, heat has to be added to it continuously to change its state from a liquid to a vapor. At standard atmospheric pressure, all the time the water is boiling, its temperature remains constant at 100 degrees Celsius until all the liquid has been transformed. If the water vapor is contained and the same amount of heat is removed from it, then it will condense back into a liquid. The greatest quantity of heat movement occurs during these changes of state, while a liquid is boiling and changing into a vapor, and when a vapor is condensing back into a liquid. This is known as latent heat. If a liquid is subjected to pressure, its boiling point is raised. Therefore, a higher temperature must be achieved to make it boil and change to a gas. Subjecting water in a closed container to a pressure of 100 kilopascals above atmospheric will raise its boiling point to approximately 120 degrees Celsius. Similarly, if the pressure in the container is reduced, then the boiling point will also be reduced. The refrigerant in the air conditioning system must have a low boiling point and must also be able to change its state in a continuous cycle of vaporization and condensation. One commonly used refrigerant, known as R134A, has a boiling point of minus 26.6 degrees Celsius. This is a liquid which boils well below normal room temperatures, and in vaporizing will absorb tremendous amounts of heat without increasing its own temperature. This vaporization must take place inside the vehicle in a unit which can become cold itself and can be positioned so that the warm air inside the vehicle can be drawn into contact with it and give up its heat. This is the function of the evaporator. Once cooled, the air can be redistributed inside the passenger compartment. Since the refrigerant must carry away from the evaporator the heat it has absorbed, a continuous flow of refrigerant must be provided. This is the function of the compressor. The compressor circulates refrigerant through the system and also raises its pressure. Pressure can only be created when there is a restriction to the flow. This is provided for at the entry to the evaporator, where the quantity of refrigerant entering the evaporator is controlled. The restriction will also cause a drop in the pressure of the refrigerant as it enters the larger volume of the evaporator. The drop in pressure ensures the liquid refrigerant will be able to vaporize inside the evaporator coils. Heat is absorbed from the air passing over the external evaporator fins into the vaporizing refrigerant. The low-pressure, low-temperature refrigerant is drawn away from the evaporator by the intake side of the compressor. The heat contained in the refrigerant must then be given up to the outside air, and it must change its state back to a liquid to continue its cycle. This is the function of the condenser. The restriction to flow at the entry of the evaporator allows the outlet side of the compressor to build up pressure on the high-pressure side of the system. The low-pressure, low-temperature vapor drawn into the compressor is discharged as a high-pressure, high-temperature vapor. The temperature of this high-pressure vapor is now considerably above ambient air temperature. The high-pressure vapor passes into the condenser coils and gives up its heat to the airstream flowing across the external condenser fins. The removal of this heat causes the refrigerant to fall in temperature, and in doing so, also causes it to condense back into a liquid. This happens within the condenser coils, and the high-pressure, still high-temperature liquid exits from the condenser to flow on through the system. While air conditioning removes heat from the vehicle interior, it also reduces the amount of moisture in the air or relative humidity in the passenger compartment. This moisture is collected in a tray below the evaporator and is drained away to the outside of the vehicle by means of a rubber tube. The reduction in the humidity of the air further promotes body cooling by the more rapid evaporation of perspiration. In a fixed orifice tube system, the components necessary for system operation are the condenser, the evaporator, the compressor, the orifice tube, the accumulator, connecting pipes and hoses, a thermostat, blower fans and pressure switches. The orifice tube is located between the condenser and the evaporator and provides the restriction to flow necessary for system operation. When the air conditioning system is switched on, an electromagnetic clutch is energized on the compressor drive plate and the compressor is driven by the engine crankshaft. Vaporized refrigerant is drawn from the low pressure side of the system by the compressor. It is discharged from the compressor as a high pressure, high temperature vapor and flows to the condenser where it is cooled by the air flowing across the condenser coils and fins. The reduction in temperature causes the refrigerant vapor to condense and turn into a liquid, which flows to the filter and then to the orifice tube. The liquid refrigerant loses pressure by flowing through the fine tube and is then forced to expand suddenly by passing through the nozzle and entering the larger volume of the evaporator. The drop in pressure causes the low pressure, low temperature liquid to boil, and this liquid mist evaporates rapidly in the evaporator coils, absorbing heat from the air passing across the external fins. The cooled air is directed to the interior of the vehicle by blower fans. The refrigerant in the evaporator flows onto the accumulator. The accumulator acts as a storage volume for the refrigerant and also separates liquid from vapor. Refrigerant vapor enters at the top of the accumulator. Any liquid refrigerant falls to the bottom. The accumulator is made from aluminium and has a large surface area. This assists the final evaporation of any liquid refrigerant leaving the evaporator. Refrigerant vapor is drawn off from the top of the accumulator through the outlet tube by the compressor. At the bottom of the outlet tube is a small hole which allows a small amount of any lubricating oil that settles at the bottom of the accumulator to be drawn to the compressor. The accumulator also contains filters and desiccants, which remove impurities and moisture from the refrigerant as it passes through. Control devices are fitted into the system to ensure maximum efficiency and to protect components from damage. A thermostat is used to sense the temperature of the evaporator fins and help ensure that they do not drop below 1 degree Celsius. If the temperature of the fins were to drop to 0 degrees Celsius or less, moisture condensing out of the air would freeze on the unit and block the airflow through the evaporator. When the fins of the evaporator drop to 1 degree Celsius, the thermostat contacts open. This breaks the electrical circuit to the compressor clutch and stops the compressor from circulating refrigerant. When the evaporator temperature rises, usually to about 4 degrees Celsius, the contacts close and the electrical circuit to the compressor clutch is restored. The fixed orifice tube cannot alter the amount of refrigerant entering the evaporator. Therefore, as extra cooling is required and the heat load on the system increases, the compressor cycles on for longer periods. As the heat load decreases, the compressor cycles off for longer. This cycling adjusts the system to the heat load. System protection against high pressures is provided by a high pressure switch mounted in the high pressure line between the condenser and the orifice tube. High temperatures and pressures may develop if the condenser is unable to transfer its heat effectively to the outside air. This may be due to blockage of the condenser fins or an inoperative electric fan. If this occurs, the high pressure switch open circuits the compressor clutch and prevents the compressor from circulating refrigerant. If a leak develops and the refrigerant is low in charge, a low pressure switch on the low pressure side of the system turns the compressor off when the system pressure falls below a set value. As lubricating oil is carried around the system by the refrigerant, This prevents damage to the compressor due to lack of lubricating oil. This section examines the thermostatic expansion valve system. In a thermostatic expansion valve system, the components necessary for system operation are the condenser, the evaporator, the compressor, the receiver dryer, the thermostatic expansion valve, connecting pipes and hoses, a thermostat, blower fans, and pressure switches. The thermostatic expansion valve, also called a TX valve, is located at the entry to the evaporator and provides a throttling or restricting function to control the quantity of refrigerant entering the evaporator. At the same time, it must provide for complete vaporization of all the liquid refrigerant which enters the evaporator. The system is charged with refrigerant and a quantity of lubricating oil, which circulates with the refrigerant at all times. When the air conditioning system is switched on, an electromagnetic clutch is energized on the compressor drive plate, and the compressor is driven by the engine crankshaft. Vaporized refrigerant is drawn from the low-pressure side of the system by the intake side of the compressor. It is discharged from the compressor as a high-pressure, high-temperature vapor and flows to the condenser where it is cooled by the air flowing across the condenser coils and fins. The reduction in temperature causes the refrigerant vapor to condense and turn into a liquid which flows to the receiver dryer. The receiver dryer acts as a storage volume for liquid refrigerant and also contains a filter and desiccant or drying material. The liquid refrigerant must pass through the filter and desiccant to reach the pickup tube where the refrigerant can flow on to the TX valve. At the TX valve, the amount of liquid refrigerant flow is determined by the action of a spring-loaded valve, which is controlled by different pressures on each side of a connecting diaphragm. The pressure in chamber A is determined by a temperature sensing bulb, which is taped to the evaporator outlet and insulated from air temperatures. The sensing bulb is filled with refrigerant and is connected to chamber A by a capillary tube. The temperature at the evaporator outlet determines the pressure in the bulb. Higher temperatures will give higher pressures, and this will tend to open the valve wider and allow more refrigerant to flow through. Lower temperatures will give lower pressures. This will tend to close the valve and reduce the flow of refrigerant. The pressure in chamber B is determined by the refrigerant pressure in the evaporator and by the force supplied from the valve spring, often called a superheat spring. The spring is designed to ensure that the temperature of the refrigerant leaving the evaporator is between 2 degrees Celsius to 9 degrees Celsius higher than the boiling point of the refrigerant at the current operating pressure. This difference in temperature is called superheat, and it ensures that all liquid refrigerant which enters the evaporator is vaporized before it leaves. When the compressor switches on, the suction from the compressor removes refrigerant vapor from the evaporator and lowers its pressure. This reduces the pressure in chamber B and allows the pressure in chamber A to move the valve away from its seat by the action of the diaphragm. High-pressure liquid flows through the orifice and enters the evaporator as a low-pressure liquid. The liquid expands into the larger volume of the evaporator, causing a reduction in its pressure, and this, together with heat from the air passing over the evaporator fins, causes it to vaporize. The temperature of the refrigerant leaving the evaporator is interpreted by the sensing bulb attached to the outlet. If the temperature is low, the refrigerant in the sensing bulb will contract, and pressure in chamber A of the TX valve will reduce. The diaphragm moves, and the valve moves towards the valve seat to reduce the quantity of refrigerant entering the evaporator. If the temperature is high, the refrigerant in the sensing bulb expands and exerts more pressure in chamber A, causing the valve to move away from its seat and allowing more refrigerant to enter the evaporator. The amount of refrigerant flowing depends on the quantity of heat to be removed from the air passing over the evaporator fins. More heat means that more refrigerant is required to remove it, Less heat means that less refrigerant is required. A number of control devices are fitted into the system to ensure maximum efficiency, and these operate as described in the section on the fixed orifice system. This section examines the electronic control unit for automatic air conditioning systems. An automatic air conditioner is a manual air conditioner and heating system equipped with sensors which detect changes in ambient temperature, cabin temperature, and solar radiation. The electronic control unit evaluates the signals from the sensors to determine the operating conditions, and outputs actuators to move dampers and valves to control the throughput, temperature, and direction of the air delivered by the system. The climate control system can be operated in manual mode, where the operation is similar to a normal heater and air conditioner system. The driver determines where the air is delivered, the volume of air delivered, and its temperature. Or it can be operated in full automatic mode. In full automatic mode, the electronic control unit receives signals from sensors and controls the flaps and valves of the heating and air conditioning systems to create a blend of air that matches the temperature that is selected by the occupants. The electronic control unit, or ECU, contains a microcomputer. It is constructed from printed circuitry and has a large number of electrical components and electronic devices. It is normally housed in a metal or plastic container, and on some automatic climate control air conditioning systems, the control panel is part of the electronic control unit. The electronic control unit receives signals in the form of voltages from the ambient air temperature sensor, the cabin air temperature sensor, the coolant temperature sensor, the evaporator temperature sensor, sun load sensor, and the control panel. The electronic control unit compares these voltage values with values stored in its memory. If a difference in values occurs, the electronic control unit changes the position of actuators. The actuators are electric solenoids and electric motors which control the position of doors and taps either directly or by vacuum servos. The electronic control unit also controls the speed of the interior ventilation fan. The speed of the fan is infinitely variable between a stopped condition and the fan's maximum speed. Some actuators provide a feedback signal to the electronic control unit in the form of a voltage signal. This signal is used by the electronic control unit to determine what position the actuators are in and whether or not they are moving. When placed in automatic mode, the electronic control unit uses the last operator desired cabin setting. For this example, 24 degrees Celsius. The electronic control unit checks the temperature of the outside air, called the ambient air temperature. This is registered by the ambient air temperature sensor at 28 degrees Celsius. The car is parked in bright sunlight, so the radiation from the sun has heated the cabin air temperature to 45 degrees Celsius. The sun load sensor registers that the vehicle is in bright sunlight. When the engine has started and the climate control system is functioning, the electronic control unit switches on the air conditioning compressor and increases the speed of the interior ventilation fan. Air is drawn into the fan either from outside the vehicle or from within the cabin. The air then flows through the air conditioning evaporator core where heat is removed. The cold air-conditioned air is directed by flaps and ducts throughout the cabin of the vehicle, absorbing heat from the vehicle cabin and occupants and thus lowering the temperature. The cabin air temperature is continually measured by the cabin air temperature sensor. When the cabin air temperature has been lowered to within approximately 2 degrees Celsius of the desired selection, the fan speed is gradually reduced. To achieve final control, the heater circuit may be opened and a blend door may be moved to direct some of the cold air-conditioned air through the heater core to provide fine temperature control. Both the fan speed and blend door openings are variable. If the vehicle is driven from sunlight into shade, less radiated heat is applied to the cabin interior through the cabin glass. The climate control system will have less heat to remove from the cabin of the vehicle. A sun load sensor located on the dash changes the signal that it sends to the electronic control unit. The electronic control unit registers this change in signal and will usually increase the amount of air that can flow across the heater core to compensate for the lower amount of heat radiated into the cabin. As the vehicle is driven out of the shadow, the sun load sensor again changes its output, and this is registered by the electronic control unit. More sunlight means more heat radiated to the cabin interior through the cabin glass, so the amount of air flowing through the heater core may be reduced. Many electronic control units have a self-diagnostic function, which assists in locating faults that may be present in the electric system of the climate control system. Fault codes can be displayed on the vehicle's display screen. Each code represents a circuit and components whose signals are outside of the limits expected by the electronic control unit. The fault codes are stored in the electronic control unit's memory until they are cleared during servicing. This section examines servo motors for automatic climate control air conditioning systems. Servo motors are used to control flaps and valves in the heater and air conditioning systems. By repositioning the flaps and valves, the output temperatures can be adjusted to the temperature desired by the occupants of the vehicle. Servos can be one of two types: vacuum servos and electrical servos. Vacuum servos consist of a sealed housing divided by a flexible diaphragm. The diaphragm seals the housing into two separate chambers. One of the chambers is open to the atmosphere. The other side is sealed and has a fitting for a vacuum hose connection. A spring forces the diaphragm towards one side when no vacuum is applied to the diaphragm. A linkage from the diaphragm connects it to the component to be moved. When vacuum is supplied to the sealed side of the diaphragm, a difference in air pressure occurs across the diaphragm. The force developed overcomes the spring force and the diaphragm moves, compressing the spring and moving the linkage. Admitting air to the vacuum side of the diaphragm allows the spring to return the diaphragm to the rest position. Some diaphragms use two sealed chambers, with neither end open directly to the atmosphere. When movement is desired, vacuum is applied to one side of the diaphragm and atmospheric air pressure to the other. The vacuum delivered to the diaphragm chamber can be controlled by a solenoid valve. When the electronic control unit wants to move a damper flap, it grounds the electrical circuit for the solenoid winding. Vacuum from a storage tank is applied through the solenoid valve to the diaphragm. To release the diaphragm, the electronic control unit open circuits the solenoid, and the diaphragm returns to the rest position. Movement of flaps and valves can also be achieved by using electrical motors that respond to output signals from the electronic control unit. An electrical servo motor is used to move the blend door. It incorporates limit switches to open circuit the motor when the maximum travel of the door has been reached. This stops the motor from burning out. Some electrical servos also utilize a carbon film potentiometer to signal to the electronic control unit the position of the blend door and, if it is moving, the direction in which it is traveling. A voltage from the electronic control unit is applied across the potentiometer. The wiper is connected by the signal wire to the electronic control unit. For maximum cooling effect, the blend door is moved to stop airflow through the heater core, and in this position, the voltage signal back to the control unit is at its lowest value. As the blend door is moved to allow airflow through the heater core, the voltage at the signal wire progressively increases until, at the maximum heat position, the voltage signal is at its highest. The control unit is thus aware of the blend door position, movement, and direction of travel. This section examines sensors for automatic climate control air conditioning systems. The electronic control unit needs to know the temperature of the outside air, the cabin air temperature, the temperature of the air conditioning evaporator, the temperature of the coolant circulating through the heater core, and if the vehicle is in bright sunlight. In most instances, the temperature sensors used in the climate control air conditioning system are thermistors. Although they may vary in appearance, their general operating characteristics are the same. These are solid-state electronic devices that change their resistance in response to temperature. As the temperature of the sensor increases, the resistance decreases. They are known as NTC resistors, as they have a negative temperature coefficient. When connected into a circuit, the sensor changes the voltage at the electronic control unit. The electronic control unit reads the sensor voltage as the temperature and compares this reading with information stored in its memory. The ambient air temperature sensor measures the temperature of the outside air. It is usually located in front of the air conditioning condenser, where the forward motion of the vehicle and the action of the condenser fans forces air over the sensor. If the outside air is cold, the resistance of the ambient air temperature sensor will be high, and the voltage at the electronic control unit will be high. If the outside air temperature sensor is hot, the ambient air temperature sensor resistance will be low, and the voltage at the electronic control unit will be low. The cabin air temperature sensor is mounted in a tube-type device called an aspirator. One end of the tube is open to cabin air, and the other is connected to the interior fan. Operation of the interior fan creates a flow of air through the aspirator. The temperature of the cabin air flowing through the aspirator controls the signal sent to the electronic control unit. The evaporator temperature sensor is located in the airstream, where the air leaves the evaporator and signals to the control unit the temperature of the air. The coolant temperature sensor for the engine management system signals to the climate control ECU the temperature of the coolant flowing in the heater core. Some climate control systems have a separate coolant temperature sensor, usually located near the engine management coolant sensor. The signal from the coolant temperature sensor is used in conjunction with the signals from the ambient air sensor, the sun load sensor, and the cabin air temperature sensor to control heater and fan operation. For example, if the electronic control unit registers the following readings: coolant temperature 16 degrees Celsius, ambient air temperature 0 degrees Celsius, sun load 0, cabin air temperature 0 degrees Celsius, the heater tap will open fully, the blend door will move to maximum airflow across the heater core, and the fan speed will be slow and steady. The sun load or solar sensor is located on the dash panel, where it is exposed to light entering through the windscreen of the vehicle. This sensor is a photodiode. It becomes more conductive as the light intensity increases. When connected to the electronic control unit, a change in light intensity is registered as a change in voltage. Other inputs to the electronic control unit come from the operator's control panel. The operator can tell the electronic control unit where to deliver air using switches which produce an on-off type signal. The unit will also receive instructions from the operator regarding the desired cabin temperature required. The desired temperature selection is used to tell the electronic control unit what temperature the operator wishes the inside of the vehicle to be. The electronic control unit then adjusts the position of valves and flaps to achieve the desired temperature. This section examines blower speed controls. The blower motor supplies the airflow to move air around the inside of the passenger compartment. It is located in the ventilation system before the air conditioning evaporator. In a manual air conditioner, the switch connects resistors in series with the motor to control its speed. The higher the resistance connected in series with the motor, the slower that motor will operate. Reducing the series resistance increases the motor operating speed. Most air conditioning systems use 2 resistors to give 3 driver-selectable speeds of the fan motor. In climate control systems, the speed of the fan motor can be controlled electronically by the control unit modulating a pulse width signal. A longer pulse width will produce a higher fan speed. The electronic control unit changes the fan motor speed automatically depending on the difference between the interior cabin temperature and the set temperature. When the difference in temperature is large, the fan speed is increased to increase air circulation through the cabin. When the difference in temperature decreases, the fan motor speed decreases. This gives an infinitely variable fan speed between 0 and maximum speed. The change is progressive. This section examines air conditioning compressors. The air conditioning compressor circulates refrigerant through the air conditioning system. It is normally driven by a belt from the engine crankshaft. 4 basic types are used: reciprocating piston, rotary vane, scroll, and axial piston. The axial piston type is one of the most common. The cylinders are placed around the drive shaft and parallel to its axis. Each cylinder has a double-ended piston, allowing a separate pumping chamber at each end of the cylinder. Each pumping chamber has a set of inlet and discharge valves. The inlet reed valves are connected to the inlet port of the compressor by drillings. The discharge valves are connected to the discharge port also by drillings. A swash plate is attached to the drive plate at an angle. Rotation of the drive shaft causes the outer edge of the swash plate to constantly change its linear position. The pistons are connected to the outer edge of the swash plate by swiveling ball joints. The action of the plate and ball joints continually moves the pistons back and forth in the cylinder. As the volume above a piston increases, the refrigerant is drawn into the cylinder through the inlet reed valves. When the volume above a piston reduces, the refrigerant is forced out of the cylinder through the discharge reed valves. As one end of the cylinder is on the intake stroke, the other end is on the discharge stroke. This dual pumping action occurs in each cylinder during each revolution of the crankshaft. This section examines air conditioning condensers and evaporators. The function of the condenser is to transfer heat from the high-pressure, high-temperature refrigerant to the outside air. In light vehicle applications, it is normally positioned in front of the radiator, where it is exposed to maximum ram airflow when the vehicle is in motion. The airflow is assisted by the engine cooling fan or by an auxiliary electric fan, and these must create sufficient airflow when the vehicle is stationary. The condenser is usually made as a continuous coil of thin tube meshed with a compact series of fins surrounding it. The fins increase the surface area available to maximize the amount of heat transferred from the refrigerant to the outside air. The evaporator is mounted in the passenger compartment and is positioned so that air from the cabin interior can be passed across its external surface. It is normally constructed of aluminium tube with fins attached to increase the surface area. This maximizes the rate of heat removal from the air. This section examines air conditioning receiver dryers. The receiver dryer is normally mounted in the high pressure line between the condenser and the TX valve. It receives liquid refrigerant from the condenser, which it stores until required by the TX valve. The receiver dryer is a sealed metal canister which contains filters to remove impurities and desiccants to absorb moisture. High-pressure liquid enters the receiver dryer and passes down through the filter and desiccant material. It exits via the pickup tube at the bottom of the canister and moves on to the expansion valve. This section examines air conditioning hoses and pipes. To carry refrigerant between the air conditioning system components, special types of hoses and pipes must be used. They must be capable of withstanding the high pressures and temperatures that are found inside the system, as well as being able to flex and withstand the vibrations and movement of the engine. Hoses are used to connect the inlet and outlet ports of the compressor to the air conditioning system. The hose connections are crimped to the hose and use special unions that must be carefully assembled to avoid leaks. Pipes are rigid tubes of metal, often found connecting components that are fixed to the body of the vehicle. All pipes must have properly formed bends and must be secured to the vehicle body to prevent fatigue cracks. The connections can be made with flared flanges or threaded unions that are welded to the pipe. The thermal expansion valve, the TX valve, is constructed of cadmium-plated steel or of aluminium. 3 types are commonly used. These are internally equalized, externally equalized, and H-block. This section examines thermostats. When warm air passes across the evaporator fins, the cooling action causes water vapor in the air to condense and adhere to the fins in the form of water droplets. If the temperature of the fins drops to 0 degrees Celsius or below, ice will form on the fins, restrict the airflow, and prevent heat being transferred to the refrigerant. A thermostat is used to monitor the temperature of the evaporator fins and control system operation within set limits. The bellows type has a capillary tube that is placed about 25 millimeters into the evaporator core so that it contacts the fins. The capillary tube and bellows are sealed and filled with a temperature-sensitive fluid, which expands and contracts with temperature changes. This increases or decreases the pressure in the bellows. The bellows is positioned to open and close a set of contacts which form part of the electrical circuit to the compressor clutch. Springs connected between the bellows contact frame and the thermostat housing try to keep the contacts open. Pressure in the bellows tries to force the contacts closed. When the temperature at the evaporator fins falls below the minimum setting, the fluid in the capillary tube contracts, reducing the size of the bellows. The springs mounted on the pivoted frame move the frame to open the contacts and break the electrical supply to the compressor clutch. The compressor stops circulating refrigerant around the system and the temperature of the evaporator fins begins to rise. This increased temperature is applied to the fluid in the capillary tube, causing an increase in pressure at the bellows. The bellows pushes on the pivoted frame against the spring force and closes the contact points to complete the circuit to the compressor clutch once more. Circulation of refrigerant is resumed and system operation recommences. The thermostat usually cycles the system between a minimum of 2 degrees centigrade and a maximum of 8 degrees centigrade to maintain the evaporator at the required temperature. This section examines air conditioning system refrigerants. The refrigerant used for many years in automotive air conditioning systems is a substance known as dichlorodifluoromethane, commonly referred to as Freon, or R12. It is one of a group of gases called CFCs. R12 has the following properties. It is non-flammable, non-toxic, is stable at all temperatures, does not react with aluminium, steel or copper, and it is soluble in mineral oils. It also has a low boiling point and vaporizes at minus 30 degrees Celsius. However, it has recently been found to be harmful to the environment, and a number of alternative refrigerants have been considered to replace R12. The most practical of these being a liquid known as R134A. R134A is a refrigerant suitable for use in automotive air conditioning systems. It is an HFC, or hydrofluorocarbon. It does not contain the ozone-depleting chlorine atom. R134A has a boiling point of minus 26.2 degrees Celsius. All its other refrigerant characteristics are similar to R12. The only difference being that its operating pressures and temperatures in the evaporator and condenser are slightly higher than for R12. There are important differences in their chemical properties. Unlike R12, R134A is not soluble in mineral oils, so new compressor lubricating oils have been developed. To prevent the wrong lubricant or refrigerant being installed during servicing, the service ports on air conditioning systems have been changed so that the service equipment for an R12 system cannot be connected to an R134A system. This section examines pressure switches. High pressures and low pressures can cause severe damage to air conditioning system components. High pressure switches are mounted in the high pressure side of the system and have their switch contacts in series with the compressor clutch circuit. If the pressure exceeds the switch setting, the switch will open circuit the compressor clutch and the compressor will stop circulating refrigerant. Low pressure switches are mounted in the low pressure side of the system and are also connected in series with the compressor clutch. Low pressures can occur in air conditioning systems when the refrigerant has escaped. With no refrigerant flowing, lubricating oil flow is also reduced, and this can damage the compressor. Low pressure causes the contacts in the low pressure switch to open and break the electrical supply to the compressor clutch and stop its operation.